Then you write down on the red column.
Oh, yeah.
On the left column.
So you want it in English, okay. I started writing in Tamil and I forgot how to start. So
in part 3.
Sort of like this one. Ooh, right? So okay, so the speaker this afternoon, yes, I need a tea before, is someone I have known for many years. Dr. Ravindran, control numerical finite element methods, implementation of it, reducing the dimensionalities is one of his specialty.
Okay, thank you for the introduction. Thank you, Palman and for. Okay, thank you for the invitation, Palman and pardon? It's okay. Okay, so I'm going to talk about boundary penalty method for Dirichlet boundary control problems associated with Navier-Stokes equation.
Can we have the battery case?
So, to put this in perspective, I'm going to look at incompressible Navier-Stokes equation. So I'm looking at incompressible Stokes, and at the boundary of this domain omega, I'm going to denote this by gamma. We have a control action. The velocity is equal to g on gamma, and so this is our control. Since it is Dirichlet, it's not variational. So there are difficulties, both computational and theoretical. So I'm going to approximate this using a penalty approach. So I'm going to penalize this and come up with an approximate formulation of this boundary condition. Okay? So let's look at the penalty formulation. To see how to properly penalize this thing and come up with an approximate version, I'm going to perform integration by parts. Okay, so let's multiply this Navier-Stokes equation by a test function. So let a test function v belongs to h1 omega. This is my my h1 is equal to this w12 omega. That people have used this notation. Okay, so let's take a test function from h1 omega, and I'm going to multiply this by v.
Is k a valid function or vector value?
All of them are vector.
It's a test function.
Yeah, a test function. It's independent of time. All of them are vector quantities. Okay, I'll talk more about that a little later. Okay, so v is also a vector function. Okay, so let's multiply this. Is that okay? Maybe I'll use integrals. Now I'm going to integrate by parts on this term. That's natural in setting up weak formulation, and also on this pressure term. Okay, and see what we get. Okay, so if I apply integration by parts, I get some boundary terms, right? Okay, minus mu with the boundary gamma du dn d ds, and we get this gradient u dot dg. And then when I integrate by parts on the pressure term, I get plus integral d dot n. Yes. Right? Okay. This one. Okay. Now I have some new terms here, right? This is new, and this one. Let me see. The nonlinear term. I have some new terms. Right? Okay. This is the boundary term, and another boundary term here. Okay. Now I'm going to introduce an approximation to the boundary condition so that I can lift that Dirichlet boundary condition, okay, into the weak form. Okay. So I have the boundary condition u equals g, right? So I'm going to reformulate that as follows. With the penalty parameter epsilon, I'm going to introduce a term here and add it to this boundary condition, okay, so that I can apply this into the weak formulation, okay. One question, yeah. Oh, sorry.
What happened to the pressure term over the omega?
Yeah. That's right. I forgot that term too. Okay. Yes. Okay. Thank you. Okay. So I'm going to add a term with a penalty parameter epsilon. That's assumed to be small. Okay. Okay, as a scale of epsilon. So that's going to be du nu du dn minus p dot n or pn. So this is the boundary penalization. Okay. So I replace this boundary condition with that new boundary condition. Okay. So this is your Dirichlet boundary condition. Introducing a Neumann type boundary condition here. Okay. Okay. With that, see, I can rewrite this integral weak form or this integral form of the Navier-Stokes equation as follows. that clear? Yeah. It's a question?
So, in the second line from bottom, you've got 1 over epsilon.
Yes. That is because of this epsilon. If you combine these two terms, yet appear this term pops up, right?
But what is epsilon?
Epsilon is a small penalty parameter.
You started from the equation where there was no epsilon, yes?
Yes. Yeah. So I modified this boundary condition and replace it with this. Okay. So as epsilon goes to 0, this disappears. So you get that, recover that original boundary condition. Yeah. Okay. So that's why I call this penalty. Okay.
Epsilon can be any real number.
Yeah.
Okay.
Typically small. Okay. So this is the weak formulation we get. Okay. Of course, we have the divergence free condition, so you can put that here. Okay. Now, there is a problem with this weak formulation. See, I'm taking V in H1, right? The problem is this formulation is not stable. Since V belongs to H1, so look at this trilinear form. Let's look at the trilinear form. Typically, when you study the stability, you use this energy analysis, right? You take V equals U and then estimate the solution. And trilinear form becomes 0 when you set V equals U, typical, with the standard functional framework, okay? Here I'm using slightly different function spaces. So let's look at the trilinear form. Let me look at a little bit of general trilinear form, and that U dot gradient U B. Let's integrate by parts. That's a technique you use to prove in appropriate function spaces this trilinear form is Q-symmetric. Therefore, when you have these two equal, that trilinear form drops out, right? Okay, so let's integrate by parts and see what sort of term this is when V is in H1. Usually it's in H1 0, right? Okay, so let's perform some integration by parts. First, I write this as in component form. Okay, let's perform integration by parts. So I get a boundary term, right? Okay, Ui n minus integral. Okay, I'm going to get ddxi Ui wk. And then Vk. This is over the domain omega. Okay, so this is equal to integral Ui now by product rule you get this Ui dxi okay, let me come back to this vector notation. So this is u dot n and then v dot w, right? That's what this is. And what is this term? Minus integral. This is divergence. And then you have w dot v minus integral. This is u dot gradient of w dot v. Okay, right? So what do we have? Let's see. Divergence of u is 0, right? Okay, so this term will drop out. Okay, assume this divergence of u is 0. We are talking about encompassed law. And my v, see, my v is in H1. I'm talking about boundary control. Boundary velocity is non-zero, so u is non-zero. Okay, so v is H1, so this term won't drop out. Right? That's why this the trilinear form here is not skew symmetric. Okay, if this drops out, see, when you swap these two terms, see, you get a negative, right? All the other term vanishes. If this v is 0 on the boundary, but my v is not 0 on the boundary. So this is not going to drop out, and this is hard to derive a priori estimates showing stability. Okay, so there is a problem with this weak formulation. Okay, and that is because of this. This is not correct yet. Okay, I'm going to modify this further so that the weak formulation become more stable. Okay, and I do this by skew symmetrizing this trilinear form. Okay, so let's see how we can skew symmetrize this. So I have divergence of u So now I'm going to multiply this by 1/2. And subtract off, sign something as one sign. So subtract off 1/2 of that term, the last term from here. Okay, so 1/2 integral u dot gradient of v minus 1/2. And I get minus integral u dot gradient of w omega. Okay. Now divergence of u is 0. right? So I can strike that term out. I should not have used here. And let's see. Okay, that's fine. So let me rewrite this. 1/2 of integral u dot gradient of b dot w minus
So you probably need to use the plug.
too low? Oh. Oh, okay. So what we have there is, let me just rewrite this thing. 1/2 integral dot grade b dot w minus 1/2 integral u dot gradient of w dot b is equal to that boundary term 1/2. So let me put that inside. 1/2 u dot n w ds minus u dot gradient of w. Therefore, now I can put V, or let me put W equals U. Okay. So I get a special case. Okay. If you multiply by -1, say, okay, put minus here. Okay. So this is the trilinear form you see here, u dot gradient u b, right? So if I include this term on the left, okay, the trilinear form is equal to this term, okay, and maybe I should keep it here. Let me keep it here. So if I include this term or add this term to this trilinear form here, then look at the left side. Left side is Q-symmetric. If you swap all this, that's a sign. Oh, it's okay. This is Q-symmetric. If V equals U, 0. Oh, okay. Yeah. See, when V equals U, see this left-hand side is 0, right? Therefore, the left-hand side is Q-symmetric, right? And if I have this term, I don't have this term there to throw this thing, right? So I need to introduce this term also in the boundary condition through penalty. Then this boundary term will appear in the weak formulation, and I can say the whole thing is equal to this left-hand side. Okay?
When you say Q-symmetric,
with respect to the last two arguments.
When you have, say, for instance, linear operator.
Yeah.
This object is Q-symmetric.
Yeah, in this sense. So you have a trilinear form like this. Okay? It's equal to minus of C of UWB. It's Q-symmetric with respect to the last two terms. Okay? If you swap these two terms, you get a minus sign.
Yeah, okay.
In that sense, it's Q-symmetric. Okay? Okay.
Boundary.
Okay. So let me go here and modify this boundary condition. Penalty of inline boundary condition. Okay. So I'm going to add this thing, epsilon times the whole thing. I'm going to introduce that minus 1/2. So I'm going to put 1/2 u dot n. Okay, u dot n u. I add that term with the penalty. Okay. Okay.
Non-linear boundary condition, yeah?
Yeah, that term is nonlinear. Yes, right. Okay, so when I add that term, so that's going to appear here somewhere. Okay, it will appear here. Okay, let me see. 1 over epsilon 1/2 dot n Let me write it down here. Okay, so now this whole thing I'm going to replace with this thing. Okay, this is the well-known skew-symmetrized trilinear form people have been using in finite elements and other things. Because in the finite element context also this problem arises because when you discretize, the discrete solution may not be divergence free. It is only weak divergence free. So people use this kind of stabilized or skew-symmetrized trilinear form. Okay. Okay. So this is my CUUB. Okay. I call this C, and this is equal to, as I proved earlier, is equal to this quantity, these two terms. Okay. So now let me write down my weak formulation. That is and I'm taking now the test function in V. Okay. What is V? Let's see. My V is also slightly different. V is equal to a divergence-free subspace of H1. Okay. Since I'm taking V to be divergence free, this term also drops out. Right? So I don't have to keep this thing. Okay. So that's why you don't see this term there. Okay. And C is that. Okay, so this is my weak form. Okay, okay. So now I am ready to write down what I mean by weak solution. Okay, I'm going to take U also in V. Okay, so I'm going to seek U in okay, L20T. Okay, I also have initial condition, right? You can put that in weak form too if you want. Let's see. Okay. So here is an assumption that I'm going to make throughout the talk. One, omega, I'm going to assume omega is bounded domain in R2. And it's also Lifschitz. Okay. So here's the definition of weak solution, what we mean by weak solution. So assume U0 of x belongs to H. Okay, now I need to define what H is. H is equal to V belongs to L to omega such that the divergence of V is 0. Okay, so I'm taking L2 initial conditions. Okay, and I have a right hand side F, right, the forcing. So let's take F to be, I could take to be L2, but I'm going to take F L2 H1 omega star, dual of H1 omega. Okay. What else I have? I have this boundary control, right? Okay, what space does it live? Okay, I'm going to assume G to be. My goal is to work with L2 spaces, okay, which are a lot more convenient than the traditional H1 half space, okay, which is a fractional sobular space, so it introduces fractional spaces to work with, right? Okay, so G belongs to L20T, L2 gamma. Okay, okay. So with this assumption, what I mean by weak solution, let me call this, let me give a number for this equation. I'm going to call this NSC or NSC epsilon. Huh? This is the penalized with epsilon. So U belongs to W0T, that's my solution space, is said to be a weak solution. I will define what I mean by W in a minute. It's said to be a weak solution of NSC, of weak solution if it satisfies, if NSC holds. Huh? Okay. Where W0T, the function space W0T consists of U belongs to L20T H1 omega such that the time derivative ut belongs to L20T. The script V. Okay, what is this? The script V, script V is a traditional V that other people have used. You have seen it already. That is set of all H10 functions such that divergence of V is 0. Okay.
Dual of V is just V.
Oh, dual of V star, sorry. Okay, yeah. Okay, so with that definition, I'm going to first prove the existence of weak solution. Okay, then we'll talk about the control aspects. Okay, so basically I want to define the control to state map. Okay. Here's the theorem. Assume epsilon belongs to the interval 0, 1. It's typically small, close to 0, so this is a fair assumption. And then I can simply say there exists a weak solution to NSC. Okay. I should not have raised that form. Let me rewrite that. And the following a priori estimates.
Read those norms I can't read. Is it 0, comma, gamma?
Yes, yeah, I'll define that. Here this norm, usually I mean, what I mean by this is L2, okay? If I put, if I'm talking about substituted norm, I will put a subscript, okay? Okay, so 0, comma, gamma is equal to the norm on that W going to be okay.
What is the thing you wrote in?
Yeah, this one. Yeah, u sub t.
Why write it across?
So when you write U norm U0 gamma, you mean simply L2 norm of the restriction U to boundary.
Yeah, right. And also we have this soup of so let's prove these a priori estimates. I'm not going to prove the existence and uniqueness. Actually, this is yeah. One. Oh, here. Oh, yeah. Solution can be shown to be unique also. I'm talking about two-dimensional system, right? So I'm going to skip the existence and uniqueness part and derive only the a priori estimates. Okay. So let's record that Navier-Stokes. I'm going to use inner product instead of integral. Okay. Let me see. Okay, so to derive these a priori estimates, I'm going to take v equals u in here. Okay. So get 1/2 and now when I said v equals u, this trilinear form is now Hughes matrix. So this is going to be 0. Okay. Okay. So I get 1 over epsilon. What is equal to 1 over epsilon. Okay. Now I can estimate the right-hand sides, right, using Cauchy-Schwarz. Okay. So I get 1 over epsilon norm G norm of U. I could do dual norm. So let me use this. Oh no. Sorry. Let me use this. Now, I need to absorb some of the terms here to the left. For example, this here, I could apply Young's inequality, but the problem in absorbing this, the term that comes up there is I don't have Poincare inequality that holds in H10, but we have this generalized Poincare inequality that, yeah. Yes. Yeah. This term?
Yeah, estimate that term more clearly in the board and show.
This term?
Yeah. Can you write it on the board? Do you write the other board? Oh, here, this one.
Oh, okay. So this is basically the integral, right? I'm using inner product now. Okay, now this is equal to, you apply Cauchy-Schwarz. Okay, so I'm keeping epsilon outside, applying Cauchy-Schwarz. So epsilon times, no more. Huh? Yeah. Oh, the other term, I'm using the dual norm here. Okay. Well. We have to use the one norm. Huh? That becomes your, right? So that's why, you know, this is less than, but I should use the one norm here. Because those two norms are not equivalent in H1, it's equivalent in H10, right? Okay, so the Poincare inequality, generalized Poincare inequality, that says lambda times.
Can you pause a moment?
Yeah.
Students understand that step? No? I think probably they have questions because it's a duality pairing, so you probably want to take a moment to explain what. Okay, right? It's quite puzzling for people to just see something that looks like an inner product and then a gradient norm appears, right? Yes. Okay, so maybe write the next step.
Oh, I see. Since it's supremum, see this is less than or equal to norm of f star of u. This H1 norm. Huh? Okay. Is that? Okay.
So you're saying that you have a Gelfand triple, yes?
Yeah. Gelfand, no, I don't have a Gelfand triple.
You don't have Gelfand triple.
No. I'm not using Gelfand triple.
What do you mean by dual?
You can define a dual.
I can define a dual, but yeah, I'm not using the standard Gelfand triple.
No, I'm not saying standard because I didn't say the Gelfand. I said a Gelfand.
Huh? Pardon?
I said a Gelfand triple.
Yeah.
Now, what is exactly you are doing in essential? What do you mean by duality?
Well, I don't need duality. I could just assume F to be L2. Okay, I'm just generalizing.
It's a continuous linear functional on H1.
Yeah.
Therefore, it belongs to the dual of H1. So dual of H1 is actually contained in H minus H, right? Because since H, yes?
Yes. Dual of H1.
H10 is contained in H1, and therefore by
But is H10 is closed subspace of H1.
Yeah.
And it is known that dual to H1 does not contain distributions. It's written in Leon's mathematical volume 1.
Dual to.
Well, I don't need this dual norm, okay? I could make F to be L2.
The point is that H01 is a closed subspace of H1.
Yeah.
So you cannot say that dual to H1 is subspace of dual to H01. Yeah, but it is
Anyway,
so coming back to York,
Yeah, I could work with L2 now. I can assume F to be L2. Okay, that's fine. I don't need that. I just make it general, but I don't need that in my analysis. Okay? Okay.
the dual pairing holds. Is this okay?
Yeah, that's okay. Yeah. Anyways.
He's taking the star space as the dual of H1, so that is still okay. It has boundary terms, but
so what is the star space? Can you repeat?
yeah, the star space is the dual of H1, right?
So you take dual of H1, yes.
So it has boundary terms, not zero.
Hmm? Yeah.
U is in B, then F is in B star.
Yeah. Anyways, as I said, we can make F to be L2 function and proceed. Okay. I'm not relying on that thing. Anyways, in my analysis, it's just for the right hand side. Okay. Forcing. Okay.
Just dual
H1.
dual to H1. Okay.
Actually, dual to H1's with the divergence free.
Okay.
Okay. So by Poincare inequality, this is for H1 omega. Okay. The standard Poincare inequality doesn't have this term because that holds only for u in H1 0. So with that, and rewrite this as
Less than it.
So I apply Young's inequality to this, I get that. Now here, okay, this is about Young's inequality. In order to absorb this term, I need to introduce nu. So let's introduce nu and apply that Young's inequality. Okay. Still, I cannot absorb this thing, but this Poincare inequality allows me to place something here on the left side. Okay. So let me do something here so that I can absorb that term. let me make this 1 over 2 epsilon. Okay. Now notice norm of gradient of u squared. Let me do something. If I do this, if I replace those coefficients with this minimum, I get norm of gradient of u squared plus norm of u 0 gamma squared. Okay. Therefore, by Poincare inequality, I can say this is bigger than lambda norm u squared, right? So this is less or equal to minimum of. Yeah. Yeah.
You are taking the Poincare inequality as non-squared or without the square?
Yeah, it's a good question. Let me see. I can put the square here.
One other question. So that lambda appearing in the Poincare inequality.
Yeah.
Is some value for that is known or just it's some constant?
This is a constant, depends on the omega, depends on the size of the domain. Yeah. Okay. Okay. So this term, okay, this is bounded below by this constant times this L2 norm of u. Right. So I can put that in here, and then combining this term, I can introduce H1 norm. Okay. So 1/2 of dt squared plus some constant times 1 norm squared.
Probably I have to point out to the students that the Poincare inequality you wrote is for boundary non-zero, right? The boundary.
Yeah. Right. So this is a generalized Poincare inequality.
The boundary term not zero, so you have that term that appears on the.
Yeah, that term appears because the VU in H1, not in H10. In H10, you get the standard Poincare inequality without this term. Okay. Okay. So I get plus 1 over 2 epsilon gamma squared. The less now equal to
You go and prove the same ideas. You prove the normal Poincare inequality, you set that term to zero. You keep it. Nice thing to prove that Poincare inequality, by the way. Right? The normal Poincare inequality you integrate from the boundary to the interior. Now you keep that boundary term, and then do the thing, and then that term, additional term appears.
right.
Maybe in the next lecture you show a proof.
Right. Okay.
Is your mic on? I have difficulty hearing. I may be getting.
This is something like a new term. Okay, so I can cancel this term or absorb it with that term. So I'll become nu over 2. And this term I should have produced 1 over 4 epsilon or something like that. Okay, anyway, so I can absorb these two terms. And the required inequality follows by simple integration. If I integrate this over the interval 0t, I will get the inequality that I want. Okay. So this is what I want to prove. Okay.
So if you slow down a moment and maybe explain to the audience. First of all, first is ut, right? The first term, us time t.
No, just you.
The first term is the moment time t, right? Anyway, but just to point out to the students that the Gibbs energy equality is the counterpart of the case where the boundary terms were 0.
Right. If the boundary term is 0, this will drop out. So is this. There is no boundary condition. Boundary condition is 0. Right? So the other important difference is the bound. Bound depends on a term involving epsilon. Okay. Okay. It looks a little strange, but. Okay, so I will come back to this point when I prove existence of solution to optimal control problem later. Okay, because the bound depends on epsilon, so you don't quite have that standard bounds that allows you to extract subsequences and so on. Okay, okay. So with that, let me formulate the control problem. So optimal control problem. So let me first define admissible control. I'm going to call it U at epsilon. This is equal to set of all admissible controls. That is basically I also want set of admissible states and controls. So let A at epsilon equals U comma G belongs to the solution space cross L0T L2 gamma such that the cos function of J is finite and comma G satisfies the weak form of the Navier-Stokes equation in penalized form. For cos functional, I take the following form. Integral of theta u, theta is a functional in u is the velocity, plus where theta u satisfies following assumptions.
Is the second integral on the boundary?
Oh yes, sorry. Theta is a function from functional from h1 omega 2 plus is convex and lower semi-continuous. I'll give you some examples. Theta of u so let me just say one condition of theta u norm of theta u So L2 of theta u. Oh no, I don't need norm there. Just theta u is bounded below by this. One norm of u minus this u0 gamma norm, bounded above by one norm of u. Okay. So examples is curl L2 norm of curl u squared. So a weighted H1 norm. So delta times L2 norm of u squared plus delta 2 squared. Okay. Those two satisfy these two conditions. Okay. So here is the optimal control problem. I'm going to call this the epsilon. Find control define a function u belong to u add epsilon such that the coarse functional is minimized subject to the Navier-Stokes equation constraint, the penalized form. Okay, so this is the control problem that we have for the penalized Navier-Stokes equation. Okay, so coarse functional of this form. I'm making some assumptions about this data. You could simply think of curl of u squared if you don't like this complicated form. So here's a theorem regarding existence of solution to this control problem. Assume the hypothesis lemma. I don't know whether I called it lemma or theorem, but anyways, the well-Posner's lemma hold regarding the initial condition and forcing and so on. Then there exists E epsilon.
Sir, just sorry. So, theta, first assumption on theta u is that it should be.
Yeah, that's a functional. That itself is a functional. Yeah.
What semi-continuous? Right? So,
Low semi-continuous.
on h1 omega, I didn't get it.
Pardon? Lower.
What semi-continuous? Right? So we usually take that variance should be bigger than the value.
Yeah.
So that I didn't get on h1 omega. How you are doing? That's how usually we define lower semi-continuous.
Yeah. I'm just assuming. Okay. It is lower semi-continuous.
Asking what is the notion of lower semi-continuity on h1 omega?
H1 no. No, I'm saying this is going from this H1 no, H1 omega.
For any Hilbert space or Banach space, you just define.
Similar.
Yeah, limit infimum of right. So I should write the definition for any. That's what he's asking. For any Hilbert space, what's the definition of lower semi-continuity?
The same definition.
That is okay.
Yeah, fx0 less than limit.
That's very fine.
Yeah. Okay. Okay. So let's prove this thing.
The question.
Yeah.
This cost function, you showed that these are two examples for the theta u that you can choose. So does they mean something in this sense that it's the energy estimation that you're minimizing, or
Yeah. Curl. Yeah. It's entropy. Yeah. These examples are motivated by practical considerations. Yeah. I will give a computational example later on for this coarse function. Okay. Why I picked it like this. Okay.
So the first one is say curl of u is what? Curl is the vorticity.
Vorticity. Yeah.
So it is the total vorticity squared in the integrated in the entire domain. All the slope. How we total the flow is. Second one is taking it as L2 norm squared plus a deformation integral. Again something. So it's a sort of motivated by trying to control the flow field distortions, turbulence.
Okay. So first thing we notice, we in lemma, in the lemma I proved, we showed an existence of solution, right? to the state equation. So by the lemma, there is in this admissible set, right? So admissible set is non-empty. Okay. Therefore, I can extract a minimizing sequence. Okay. So there exists a minimizing sequence. UN Gn. That is limit of A of UN Gn, n approaches infinity, is equal to infimum of JUG such that U comma G belongs to AD. Okay, this is what we mean by minimizing sequence. Okay. Okay. Now, UN and Gn, this minimizing sequence, satisfies the state equation. Okay. So, and therefore, by the lemma and the a priori estimates, I have bounds for UN and Gn. Okay, so what is that bound? Let's see. So I have this. Also, from the cost functional, I have bound on the control. Right? Because cost function is finite. So from the cost functional, J, we have what? The cost function has a L2 norm of G, right? So I have this. This is bounded. Okay. Okay. Therefore, see, UN is bounded in this or with respect to this norm, right? Because cost functional gives us bound for this. Okay. So I can extract subsequence. Therefore, therefore I can extract subsequence, again denoted by un gn, that converges, say to u star g star. Okay. Now I'm going to take this subsequence. I'm simply using un gn for the subsequence also. I'm going to use this. Let me converges to u star. It converges to. So let me write this statement. So un converges to u star in L2 0ph1 and un at the boundary converges weakly to u star at the boundary. Okay. And this weak convergence can be converted to strong convergence. Because of a compact embedding, since L2 0t, H1 is compactly embedded in L2 0t. This weak convergence becomes strong convergence in L2. So un converges to u star. Now it's a strong convergence in L2 0t, L2 omega. Okay. Now with that, I can go to the weak form that this un gn satisfies and take limit term by term. Okay, that's the idea. For example, so now you can take limit
What is your first line? What did you write in the first line?
That is not correct.
The first line, since.
oh this thing,
Yes.
yeah.
What is written? Since. And what is after since?
So it's embedded in L2 0 to L2 omega.
But what is on the left hand side? No, I mean, is it
Double, what is double arrow?
Double arrow is compact embedding.
False.
It's not true?
What is the space on the left? I cannot see the first
For
letter.
example, it shows that it is 0.
Is it L2?
Yeah, that's L2, yeah.
0T H1 in L2 0T L2 is compact?
It is false.
Anyways, I don't, I don't need that shit to take limits, okay?
Just need weak convergence.
Yeah, I just need weak convergence.
Lower semi-conductivity is good enough.
Yeah.
And the weak convergence is enough, okay?
Yeah, you have the old estimates there, all of them will give you weak convergence.
Right. So I can go ahead and take, because I'm working with weak form.
You need one strong convergence for the nonlinear by trilinear form.
Yeah.
That comes from W being bounded.
So this thing converges to gradient of u, gradient of v, or u star, because un converges to u star weakly. Okay. Similarly, okay, that the nonlinear term. This thing requires some calculation. So let me go through it a little quickly. this is equal to let me add and subtract. So I'm simply added subtracted one term here. Now by triangle inequality, this becomes okay. Now if I apply Holder's inequality on the right side, it becomes well, I can one. Yeah. Okay. Yeah.
Emphasize what you got. You have the estimates now. You need to
Yeah,
argue that following the same proof as the Navier-Stokes.
Right. Taking limit term by term and show the U star G stars indeed satisfies Navier-Stokes equation.
You can do it next.
Yeah.
Thank you. Question, comment? Question. Two questions.
Maybe, okay, I will maybe discuss after because it will be long.
Okay.
No, I'll also discuss.
Okay. Any other questions, students? Comments? Good. Thank you.
Yeah. But I don't need that. Okay. I will show you.
Dual has boundary.
May have to write down the C, the complicated C I'm using. Okay.
What I understand is
Boundary.
this lemma. Sorry, you are the first.
No, that is false. I can be a simple.
No, I know that.
Yeah,
is
but you don't need that.
I don't need that.
You don't need that.
No, I'll tell you why the algorithm. There's a paper with Remo.
Yeah.
Quoted house, 70-page paper.
Yeah.
There is
Ah, yeah. So, yeah.
Yeah,
So,
the
but you don't
time,
need it because
L2
you
in
have-
time,
once
yeah.
you have,
It's false.
yeah.
Question is about
But
your
you
lemma.
do this is the idea.
So when you have your weak, so suppose you have your weak solution.
The cost
Why
function is
does
not
it satisfy your inequality?
What?
Why does it satisfy your inequality?
What you do is
Post functional?
So you say you are using lemma.
Yeah, the post functional or
No, you have weak inequality and then you have a lemma. You can replace W0.
yeah. Right. Yeah. Meant?
Yeah, because my problem is that how do you
so this is K.
Yeah, that B, yeah. How do I prove?
So how do you prove this inequality?
How do I prove this thing?
No, that is my problem.
Okay. I'll
So how
prove
do you
this thing.
prove- yeah?
Okay, I prove that L2 norm, right? Okay, this thing,
So you have
this
a
norm.
weak solution.
Let's look at the definition. Huh? This is.
I remember the definition. You
Oh,
have-
okay. So it has two.
We have a weak definition, a weak solution. So what do you do with the weak solution? How do you prove the weak
Do this, right?
talking about the U star being the solution is what
Um,
I'm going to show. Okay, so you have this one.
Did I prove? I proved this. In L2 norm, this is bounded, right? I proved this.
No, 0T B dash.
You have no.
I proved this thing.
The whole entire energy is
How do you prove this?
then this no.
I did the integration.
Can you do it again?
Sure.
Is R. These guys are finite. And therefore this
So you have your weak
solution. This term is okay.
linear term is not a problem.
Yeah. So this one.
You have a weak
Then you
solution.
need to go to the Ravindran lemma. So that says that if you in L2
Made this, right?
Etc.
and your T J Leon 0T B dash, then this is compatible with
V
0T the
plus 1 over epsilon.
so that is so once you have so those steps are identical for Navier-Stokes so this is my
V.
first paper.
Think of this L2.
How do you prove that?
Set V equals U.
What the rod is that? What the rod is only this.
Yeah. No, you need local motors. You can do reprove the whole thing without disembedding. By this is local.
What?
Oh, because that you will like
Yeah, that's gone.
you.
And this becomes